And now for something completely different, IJ form. At first, you guys aren't going to like this because it's going to look like, well, it is a different way of doing the same thing we've been doing. But I'm here to sell you IJ form today because in many ways, symbolically, it's better. It's a better way to represent vectors. But you're going to be reluctant, so just have an open mind, right? So IJ form. So let's take the vector in component form 5, 8. 5 is your delta x, your first component. 8 is your delta y, your second component. Would everybody agree I could separate it like this? I could separate it as a vector addition 5, 0 plus 0, 8. Does everybody agree with that? Okay. I could further separate it into a couple of scalar multiplications. Break it down would maybe be a better word. The first vector I could represent as 5 times the vector 1, 0. Whoops. And then doing a similar thing, how would you represent the second vector? 8 times 0, 1. Okay, 1, 0 is called the vector I. It's not the complex number I, it's different. 0, 1 is the vector j. So 1, 0 is I. I put some books will use I with a hat over it, or just bold print I. I use I with a little half arrow over it. And then 0, 1 is j. If you were to draw them in the xy plane, then 1, 0 would look like this. 0, 1 would look like this. They are perpendicular vectors, right? So I'm saying I can write 5, 8 in terms of these two perpendicular unit vectors. I can write 5, 8 as 5i plus 8j. So for any vector, let's say v, I'm going to go back to AB, components AB. Any vector in the plane, v, we can write v equals what? In IJ form, it would be what? Well, what did we do to write 5, 8 in component form? Ultimately, we just took 5 times I and 8 times j and added them together. So in this case, it would be a times I. In the more general case, a times I plus b times j. So any vector in the plane can be written as a linear combination of vectors I and j. This guy in red down here, I. This guy pointing to the right is I. This guy pointing up is j. Okay, in this example, we're going to let u be the vector 3i minus 2j, which is in component form is what? 3, 2. 3, negative 2, right? And v is the vector negative 5i minus 7j, which in component form is negative 5, negative 7. So, but we're writing both of these in IJ form. Find 2u minus 4v. Okay, let's fill in, let's substitute in what u is. Don't change to component form. That would be spinning your wheels. You'd be doing a lot more work than you need to do. So just write it, leave it in IJ form. So 2u would be 2 times, okay, use parentheses for multiplication, 2 times 3i minus 2j. That's the 2u. And then minus 4v. 4v would be minus 4v would be minus 4 times negative 5i minus 7j. So all I'm doing is substituting. Does that make sense so far? Now think about it. What property that you've been learning about since pre-algebra is scalar multiplication going to look like here when I do the multiplication first? what property is it going to look like? Begins with a D. It's going to look, scalar multiplication here is going to look like distribution. Now that's a powerful thing because we're blocking memory once again, not blocking it out, we're grouping memories together. You guys know all about the distribution property. And even though it's scalar multiplication, it sure looks like the distribution property. So, okay, so we do that. Scalar multiplication looks like regular old distribution, and you do the scalar multiplication first, right? So what do you get for when you multiply 2 times u? 6i minus, bless you, 4j, right? Okay, and then what do you get when you do, well, I almost called it distribution. When you scalar multiply by, you can think of it as plus a negative 4, I guess. What do you get? Plus 20i plus 28j. But wait, there's more. I'm really selling you this. Now, when you add the vectors together, what is it going to look like from algebra? When you add corresponding components, it's going to look like what? Well, what did you call it in algebra, in beginning algebra, or algebra 1? You're adding like terms, right? Because when you add corresponding components together. Well, you're going to add the I components, or the numbers in front of the i's together, right? You're going to add the numbers in front of the j's together. It looks like we're adding x's, like x's and like y's together, right? Or something like that. And so the analogy continues then. So if you have 6i plus 20i, what's your new first component? Some books will call it your I component. What's your I component? It's 26, and then you have the I there. And that's your first, 26 then is your first component of the resulting vector. Plus, you have minus 4j plus 28j plus 24j. So that's my sales pitch to you guys. The reason why IJ notation is superior to the other notation, especially when you're doing a lot of symbolism, symbolic work, looks like algebra. It's nothing new when you think of it, at least symbolically. So the mechanics work exactly the same. And you might actually be less likely to make mistakes when it's in this form. Okay, magnitude of V. So V was negative 5i minus 7j. You can immediately identify the first and second components, which are what you use to find the magnitude. What's the first component of V then? Negative 5. What's the second component? Negative 7. So the magnitude or length of V, remember we take the square root of something squared plus something else squared. What are those somethings? Yeah, so negative 5 squared. Underneath the square root, negative 5 squared plus negative 7 squared. And I didn't put the magnitude bars around it yet, so let me do that. And what do we get? 25 plus 49 underneath the root. What is that? Root. Yeah, so root 74.